Hi everyone, my name is Todd Springer. I'll be your instructor for today. The topic we're going to talk about today is refrigerators and their thermodynamics. So again, this is the topic. It's from Schroeder section 4.2 about refrigerators. So this one, and then at the risk of alienating the audience, I'll make a 1980s NFL joke, which is, this guy's name is William Perry. He played for the Chicago Bears and his nickname was the refrigerator, or simply the fridge. So that's what we're going to talk about today. I understand you've talked about heat engines. So you understand that a heat engine is a device which converts heat into work. You take heat from some hot reservoir, something hot, you use it to do some work, and then you exhaust some heat into something cold. This engine has an efficiency, which we defined as what you get divided by what you pay for it. That's the work output divided by the heat you put into it. The conservation of energy tells you that the amount of energy I put into this engine has to be equal to the energy that comes out. So the energy coming in is the extracted heat from the hot reservoir. The output energy is the work and the heat dumped into the cold reservoir. And then hopefully you learn that there's a maximum efficiency of this engine. If I have two reservoirs, TH and TC, the most efficient engine you can make has this efficiency, which is called the Carnot engine. I'm going through these again briefly because most of what we do today will be similar story, just for the different device, which is the refrigerator. So a lot of these arguments are going to come back again in a different context with a different device. So what I'm hoping that you get out of this lecture today is to understand the purpose and the basic schematic of a refrigerator. I'm not going to talk about the details of how a real refrigerator works, but I'm going to talk about a cartoon, just the basic schematic of what it is designed to do and what are the basics of that. I want you to understand how to evaluate the effectiveness of a refrigerator, which is what we call the coefficient of performance. And then we're going to learn about the limits of the coefficient of performance placed by the second law. So let's start with the second law. It's always a good place to start. Here's Clausius's statement of the second law. I'll just read it. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. So there is Clausius right there. He looks a bit like Ebenezer Scrooge, one of the founders of thermodynamics. Every time I research one of these scientists from the 19th century, I always find something interesting. This is from Wikipedia. I found that this foundational member of founded thermodynamics had a tribute created for him in 2009, which is a stone outside of this university here. And I was just a bit struck by that this man basically laid the foundation for the Industrial Revolution by studying heat engines and things like this. And then the best we can do is get a rock here 130 years after his death, or 140 years after his death. I think we can do better. I think Clausius deserves a statue. I don't know about you. So anyway, back to this second law. It's impossible to construct a device which produces no effect other than the transfer of heat from a low temperature body to a high temperature body. Now, the first time you read this, you probably think, wait a second, this doesn't sound right to me, because I have a device in my kitchen which does exactly this. It transfers heat from the inside of the refrigerator to the outside. So that seems like it violates the second law. So maybe you can pause and think for a second. Both of these things can still be true. The second law of thermodynamics is true, as Clausius stated it, and yet refrigerators can still exist. What's the catch here? The catch is that this important little piece here that says produces no other effect than the transfer of heat from a low temperature body to a high temperature body. In other words, it can't occur spontaneously. The heat cannot go from something cold to something hot. But there's another effect on the world, which is that it requires, your fridge has to be plugged in, and so it's extracting some energy, some electrical energy when you plug it in there. So the fridge can work, can function, provided you plug it into the wall, and it requires work to transfer the heat from the cold thing to the hot thing. So here's our schematic for a refrigerator. It's the same as a heat engine, but with all the arrows reversed. Okay, so now I'm providing the work. I plug the fridge into the wall, so work is now the input. What I get is I take some heat from the cold reservoir, which is the inside of the refrigerator, and then I dump some heat into the hot reservoir, which underneath your fridge you feel hot air coming out because you're dumping heat into the room, which is a hotter reservoir or a hot reservoir compared to the inside of the fridge, which is the cold reservoir. This can't happen spontaneously. You have to plug it in. You have to have the work coming in order for this to function. A little quick note, because the signs are confusing, that all of these quantities are defined to be positive. Okay, so QH is a positive number, QC is a positive number, W is a positive number. So all of those quantities are defined to be positive numbers. Now, how well does your refrigerator perform? We can evaluate that quantitatively. It's like the analogy of, or the analog of the efficiency for an engine. It's what you get divided by what you pay for it. And in this case, what I get is I get heat extracted from the cold thing, and what I pay for it is the work that I have to do. Okay? So what I get is QC. That's the goal of this, is to remove some heat from the inside of the fridge and keep it cold. And what I pay for it is the work done, right? The W. This is different than the efficiency of an engine. Okay, so remember, for an engine, the goal was to do work, and what I paid for it was heat from the hot reservoir. Just to emphasize that a little bit more, again, for a heat engine, what you get divided by what you pay, that's work divided by the heat input. For a refrigerator, what you get is QC, and what you pay for it is W. So those are different definitions of the effectiveness of these devices. And because of that definition, the range of possible efficiencies is different than the range of possible coefficients of performance. So if my engine did no work, it would be a terrible engine, and it would have zero efficiency, right? If W is 0, the numerator is 0. On the other hand, if I could somehow just construct a perfect engine which perfectly converted heat into work, by the way, you can't do this, as you learned last time, that violates the second law of thermodynamics, but putting that aside for now, if you could make a perfect engine, this E would be equal to 1, but it's not possible to get E equal to 1. The refrigerator, think about it similarly. If my refrigerator didn't do anything, it didn't pump any heat, then its coefficient of performance would be 0 because this QC would be 0. On the other hand, if I could somehow make a perfect refrigerator which pumps heat with doing almost no work, then my coefficient of performance would get really big, right? Because if I didn't have to put in very much work, W would be a small number, and if I have 1 over a small number, that becomes a really big number. So my coefficient of performance can go between 0 and infinity. Just to reiterate that, based on the first law only, your efficiency can range from 0 to 1, but your coefficient of performance can take on any value between 0 and infinity. Of course, I can't actually make efficiency equal to 1, and I can't make the coefficient of performance equal to infinity, and we'll talk about why. That's because of the second law. But I just want to get across that different measurements of the effectiveness, and they have different possible ranges. Okay, now let's think about the first law, again, in analogy with what you did with heat engines. Just think about the conservation of energy. The energy in is the work added plus the heat extracted. So those are the arrows coming into the gray box, which is the refrigerator here. Has to be equal to the energy going out of the gray box, because I can't create or destroy energy. So that means that the energy coming in, work plus QC, must be equal to the energy coming out, which is QH. So that gives me this relationship here. Just conservation of energy, energy in has to be equal to energy out. I can use this relationship here to write my coefficient of performance in many different ways. So I have 3 variables, Q, C, QH, and W. And I've got this relationship at the top here, which I can use to remove one of the variables, whichever one I choose. So I'm going to use it to remove W. So instead of writing coefficient of performance as QC divided by W, I'm going to write it as QC divided by QH minus QC. So I remove W, and I have an expression here which has the coefficient of performance, which depends only on the heat extracted from the cold reservoir and the heat dumped into the hot reservoir. This last step here is a little algebraic simplification. So if I take the top, QC over QH minus QC, and I multiply the top and the bottom by 1 over QC, I don't change the value because I multiply the top and the bottom by the same thing. On the top I get 1, and on the bottom I get QH over QC minus QC over QC, which is 1, right? So this is equal to 1. And so that's how I derived that last step there, just doing some algebraic simplification. Just to remind you again, a high coefficient of performance means the device performs well. A low coefficient of performance means the device does not doing a great job. So for example, if the amount of heat that I extract from the cold reservoir is approximately equal to the amount of heat I dump into the hot reservoir, that means I had to do hardly any work, right? If this number is approximately equal to this number, then I didn't have to apply hardly any work, right? So if these two things are very close to each other, that number that I just circled is a little bit bigger than 1, but just a little bit bigger than 1. If I subtract 1 from it, this denominator becomes very small, and 1 over a small number means that my coefficient of performance is very big. Okay, so that's good. On the other hand, if the heat QH is much bigger than QC, that means that I had to do a lot of work, right? So if this number here is much bigger than this number, that means that the work done must have been very big. And if that's the case, then this thing here would be a really large number, -1, which is, so a huge number like 1,000,000 minus 1 is still pretty close to 1,000,000. 1 over 1,000,000 is a very small number. So then your coefficient of performance would be low. And that's basically not what you want. You want a high coefficient of performance. Okay. So just the purpose of this slide is to remind you, high coefficient performance is good from the point of view of making a good effective device. Low coefficient of performance is not great from the point of view of creating an effective device. Now let's talk about that pesky second law, the second law which says that the entropy of the universe has to always go up. We're going to see that this places a limit on the coefficient of performance of the refrigerator, in the same way that it placed a limit on the efficiency of a heat engine. So let's start with the second law. Here's one statement. It's different than the Clausius statement, which I mentioned earlier. There's lots of different ways of stating the second law. So here's maybe the most concise way of stating the second law. The entropy change of the universe can never decrease in any process. In other words, whenever I do anything, the entropy of the universe will go up or stay the same. So this process here, I'm going to do this. I'm going to have my refrigerator take some work, extract some heat from the cold thing, dump some heat into the hot thing. And in that process, the entropy change of the universe must increase or stay the same. Right? It can't go down by the second law of thermodynamics. Important to remember that the second law tells you that the entropy change of the universe goes up, not any one piece of the universe. Right? So I have to think about everything involved in order to think about the entropy change. So in this process, I've got the change in entropy of the refrigerator plus the change in entropy of the surroundings, which are the hot reservoir and the cold reservoir. Add up all of those entropy changes, it has to be positive. Right? So let's do that. Let's work out each one of these things in turn. What's the entropy change of the refrigerator in one cycle? So maybe you've seen these PV diagrams. Here's an example of a cycle. It doesn't matter what this looks like. I'm just using this as an illustration. Maybe you start here, and then you go down like this, and then up like this, and then over here, and you come back to where you started. So by definition, a cyclical process starts and ends at the same point. But entropy is a state variable. So if I'm at state A, that means the entropy is something. And then if I go around this loop and I end up back at state A, the entropy is still the same as it started with. Right? So in other words, because entropy is a state variable, if I start and end at the same points, my entropy change will be 0 for this refrigerator. So remember, change in entropy is S final minus S initial. That'll be 0, assuming I start and end at the same points, which is what I do in an engine or a refrigerator. It's a cyclical process. Okay, so this part is 0. The interesting part comes when we think about these other ones, right? Like what is the entropy change of the surroundings, the hot reservoir and the cold reservoir? Okay, so let's start here. Maybe you've seen this formula before. The change in entropy of something is the heat added to that thing divided by the temperature. And then I have to do an integral here in case like maybe the temperature is changing throughout this process. Now in this particular case, the temperature won't be changing, so it'll be even simpler. So delta S is dQ divided by T. dQ is the heat added to the hot reservoir. T is the temperature of the hot reservoir. So that's how I understand this formula here. The change in entropy of something is the heat added to that thing divided by the temperature of that thing when the heat was added. Okay. if I'm adding a bunch of heat, have to add it a little bit at a time and add that up with the integral. Okay, this integral is very simple to do because by definition, the reservoir has a constant temperature. It's like if I dump a cup of hot water into the Pacific Ocean, I added some heat, but the temperature of the ocean didn't go up because it's so big. I can add a little bit of heat and then the temperature, it's not effective at changing the temperature because the reservoir is so large. So the temperature of the reservoir is constant. It remains at TH the whole time. And so this T is a constant. I can bring it outside of the integral here. It's equal to TH, right? And then the integral dq is just Q. That's the total heat added to the hot reservoir, which is what we're calling QH. Okay. So the change in entropy of the hot reservoir is QH divided by TH. How about the change in entropy of the cold reservoir? Same idea. So what's the change in entropy of the cold reservoir? That's the heat added to the cold reservoir divided by the temperature of the cold reservoir. Start with the same formula. Once again, the temperature of the cold reservoir stays constant. It never changes because it's a big reservoir. And so the T can come outside of the integral. Bring it out front. And the integral of dq is just the total heat added to the cold reservoir. Now there's this one confusing thing, which is that no heat is being added to the cold reservoir, it's being extracted, right? QC is a positive number, which is being extracted out of the cold reservoir. So how much heat is being added to the cold reservoir is minus QC. So that's why there's this minus sign here, because heat is not being added to the cold reservoir, it's being removed from the cold reservoir. So the entropy change of the hot reservoir is positive. This is positive. The entropy change of the cold reservoir is negative. But the total entropy change of the universe has to be positive or equal to 0, which tells you that the amount of entropy change of the hot reservoir is bigger than the decrease in entropy of the cold reservoir. I can rearrange this equation, which we've just derived, by putting the QC and the TC on the other side. Tells me that QH over TH is bigger than or equal to QC over TC. And then I could put all the Q's on one side and all the T's on the other side, and I have this relationship. So QH over QC is bigger than or equal to TH over TC. Let's use this to see what happens to our coefficient of performance. These formulas here are things I already derived. So this is copied from earlier when we were defining our coefficient of performance. And now let's use this relationship down here, which I just derived, relating QH over QC to TH over TC. When I use this inequality that I just highlighted, I end up with a limit on my coefficient of performance. It's given by this equation in the green box here. The coefficient of performance has to be less than or equal to TH over TC minus 1. And in case the inequality confuses you, like why is it this way and not the other way, just think carefully one step at a time. So we know that QH over QC is bigger than TH over TC, right, according to this formula here. But it's in the denominator, right? So that means the denominator of the left side is going to be bigger than the denominator of the right side. But that means that the whole thing on the left side is going to be smaller than the thing on the right side because it has a bigger denominator. Okay. So that's my maximum coefficient of performance. The best performing fridge between these two reservoirs has this maximum coefficient of performance given by this formula here. Let me summarize. We've talked a bit about refrigerators. It's basically a heat engine in reverse, takes in work, uses it to extract heat from something cold and dump it into something hot. The conservation of energy gave us this relationship between the energy input equals to the energy output. The effectiveness of the refrigerator is given by this formula for the coefficient of performance, what you get divided by what you pay for it. And then by thinking about the entropy change of the universe having to be positive, in other words, the second law must be true, given two reservoirs at TH and TC, the refrigerator with the highest coefficient of performance acting between those two reservoirs has this coefficient of performance, 1 over TH divided by TC minus 1. So I'll thank you for your attention, and we will pick it up there in class. We'll try to do some problems and go a little bit deeper into some of these issues. So thanks again, and bye for now.